Welcome to the video lecture series for Texas A&M University, course Math 150. Today we will look at section 1.8, Combinations of Functions. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. When we are talking about combinations of functions, there are four main ways using arithmetic that we can combine the functions. We can add, subtract, multiply, or divide two functions. So then we're looking at the sum, the difference, the product, or quotient. When we are finding new functions, one of the first things we want to look at or consider is the function's domain. So we will look at basic functions in combination and what is the resulting domain. When we are finding the domain of the new combination function, sum, difference, product, or quotient, we need the intersection of the individual domains. So let's let d subscript f represent the function f of x's domain, and let's let d subscript g represent the domain of g of x. So then the sum, the difference, and the product of these two functions, namely f of x plus g of x, f of x minus g of x, and f of x times g of x, will have a domain that is the intersection of the two individual domains. The quotient domain is a little bit different because as soon as we have a quotient, we automatically have a denominator. And the denominator has a restriction anyway. We know that denominators cannot be zero. So we don't just have the basic intersection of the two domains, we also include the intersection that the denominator, or g of x, can't be zero. Let's take a look at an example. In exercise 1, we have two functions, f of x equals the square root of x plus 1, and g of x equals 3x minus 6. You might want to pause the video at this point to make sure that you know how to draw this graph from using transformations. So consider the basic or parent function, y equals square root of x, and apply the transformation. According to this equation, what transformation exists on the basic square root of x graph? In this case, we would have a horizontal translation of -1. So we would move the basic square root graph one space to the left. You should also be very quick at sketching linear equations, y equals mx plus b. Here we have a slope of 3 and a y-intercept of -6. Both graphs should take you about 10 to 15 seconds. Okay, now let's consider the domains of each of these functions, their intersection, and their intersection with the intersection that g can't be 0. So in part A, the domain of f, we look at the function f and we see that we have an even radical, or square root. The radicand of the square root cannot be negative, so x plus 1 must be greater than or equal to 0, and this linear inequality can be solved algebraically to get x equals -1. And so that's it, the domain of f. In part B, the domain of g, well, we have g as a linear function, and there's no restriction either looking graphically or from the conditions that denominators can't be 0 or radicands of even roots cannot be negative. So here we have no restriction and x is contained in the reals. In part 3, oh, this shouldn't be part B, this should say part 2. Let's clear that up. This is part 2 and this is part 1 of part A. In part 3 of part A, we want to come up with the intersection of df and dg. So imagine we've got blue and red. This means that the intersection has to be both blue and red. Again, intersection means and. And in this case, the intersection of df with dg is the set x greater than or equal to -1. In the last part of this question, part 4, we want to talk about the intersection of f domain, g's domain, and the set where g of x is not equal to 0. So when g of x is equal to 0, that is referring to the x-intercept. So we're talking about not the x-intercept. So if we set 3x minus 6 not equal to 0, this tells us that x is not equal to 2. So from here, we can refer to df intersected with dg, intersecting with g of x not equal to 0. Just going to put that in curly braces. So df is the blue set of x greater than or equal to -1, intersecting with the red set of x contained in the reals, intersecting with the last set that we had, I'll put it in green, x not equal to 2. And so we need all of these colors to be true. So you could either sketch them on the number line or understand it without sketching it. If I put it on a number line, we would have, in fact, I should use red for the number line because that would be all reals. So x is all reals intersected with x greater than or equal to -1, intersected with, the green really says everything except 2. So the green really says this. And so what values are blue and red and green? Well, it's from -1 inclusive up to 2 or from 2 greater. So our set here would be x contained from -1 to 2, including -1 but not 2, or from 2 to infinity. And that would be our final set here, number 4. All right, going on to take a look at the sum of f of x plus g of x, we can determine the sum and then state the domain. So we take a look at part B. F of x plus g of x is equal to the square root of x plus 1 plus 3x minus 6, and its domain is going to be the intersection of the domain of f with the domain of g, which we saw already is x greater than or equal to -1. Now you can check this by drawing the graph and just seeing what are the x values that make y defined. So if we have y equals the square root of x plus 1 plus 3x minus 6, the graph is defined only when x is greater than or equal to -1. All right, in the next part we're looking at the difference in part C. So we have f of x minus g of x, and we get the square root of x plus 1 minus 3x minus 6, so the negative would have to distribute, giving us the square root of x plus 1 minus 3x plus 6. Again, the domain of this function is the intersection of the two individual domains, which is the same set. And if we look at the graph, we can see not much is going to change algebraically. The graph will look a little bit different, but the domain is still x greater than or equal to -1. In part D, we are looking at the product of the two functions. And so f of x times g of x is, I'm going to write 3x minus 6 first, times the square root of x plus 1, because it doesn't matter when we multiply which number comes first or which function or expression comes first. And the domain is still the intersection of the domain of one with the domain of the other. Let's confirm by looking at the graph. So we have that times 3x minus 6, and still we see the domain, different graph shape altogether, but the domain is still when x is greater than or equal to -1. And the last case we want to look at is the domain of the quotient. So for the domain of the quotient, we have to consider something a little bit different. The quotient, it does matter the direction of the quotient, and it says f of x over g of x. And so we are going to get the square root of x plus 1 in the top, all over 3x minus 6. So here the domain is going to be the intersection of the domain of f with the domain of g, with the denominator not equal to 0. And since we did this one already, we saw that this means, this case, the domain of f, the domain of g, and the denominator not equal to 0, so this is our domain. X is contained from -1 to 2, union 2 to infinity. Or otherwise, greater than or equal to -1, but exclude when x is equal to 2. Now let's take a look at the quotient function just to confirm the denominator, or the domain rather. And we can see that x equal to 2 produces a discontinuity because the discontinuity is an x value that makes y shoot up to positive infinity or down to negative infinity. We see that this is an infinite discontinuity or a vertical asymptote. Okay, let's move on to exercise 2. We want to now talk about a fifth way of combining functions. But first, let's just recall from our previous algebra courses. If f of x is 3x minus 4, let's evaluate f of negative 5. The function notation is useful because everywhere that we had x, it's getting replaced with negative 5. So here we have 3 times negative 5 minus 4, which equals negative 15 minus 4, which is negative 19. In part B, we're going to replace x with x squared. So f of stuff is equal to 3 times stuff minus 4. In this case, in part B, the stuff is x squared. So 3 times x squared minus 4 is another function or expression, 3x squared minus 4. And in the last case, instead of giving you a function name like x squared, here we're giving you functional notation. So part B, we have f of g of x, but we can substitute g of x with the square root of x. And again, the function f says to take the stuff, multiply by 3, and subtract 4. In example part 3, the stuff is the square root of x. So 3 times stuff minus 4 becomes 3 square root of x minus 4. Okay, that's just reminding us how to perform composition when you have a substitution for the input that's different from x. So the operation of evaluating an outer function at an inner function, like f of x squared or f of g of x, is a new combination of functions called composition. So we had 4 combinations. We had the sum, the difference, the product, the quotient. This is the 5th one, called composition. The outer function is f, and the inner function is the squaring function. X is still the input, but the function is the squaring function. That's why when we have the functional analysis template, you have to state the function in words, which is not using the letter x. So the function x squared, or y equals x squared, we don't call it the x squared function, we call it the squaring function, so that it's really independent of what we call the input. Okay, the resulting function is known as a composite function. If we reverse the process of composition, we decompose. So it's the process called decomposition, breaking apart into the inner and outer functions. So in exercise 3, we actually have 3 functions being composed. We have an innermost function h, a middle function g, and an outermost function f. So if we want to decompose this, we need to work from the inside out. X is the input, and we can see a linear function 5x minus 1. This could be the innermost function. But we could also put this bubble, or let statement, substitution variable, we can also put it around the absolute value. So I'm going to do that, and so I'm going to let my inner function h of x be the absolute value of f of 5x minus 1. If we do that, then we see what we have is the cube root of 2 times, well, we could let a, like we do for transformations, equal this expression. So this would say 2 times a plus 7. So that we have an inner function here, 2a plus 7. But we need to use the same variable here, so that would be called 2x plus 7, where x is now this input substituted here. And lastly, if we have a bubble around 2a plus 7, the function that's left is the cube rooting function. And the cube rooting function is applied to stuff. Here the stuff is called x. So this is one example of how we could compose this function into its individual functions. It's not the only way. We could have broken this function apart. For example, calling h of x equal 5x minus 1. Then g of x could have been 2 times the absolute value of x plus 7. And lastly, we could have had f of x being equal to the cube root of x. There's lots of different ways, and there's not necessarily one right way over the other, just some ways may be easier or more obvious than others. Alright, so now let's take a look at whether the order of performing composition, f of g of x or g of f of x, whether it matters. What we want to know is composition commutative? We know that 3 times 5 is equal to 5 times 3, and therefore the order of multiplication does not matter. Multiplication is commutative. However, 3 divided by 5 does not equal 5 divided by 3, so division is not commutative. So we're going to take a look at order of composition. Let's work out f of g of x. That means that we are going to substitute the g of x expression or function into the f or outer function. The f function verbally says take the stuff, multiply by 4, and then subtract 1. So we take the stuff, we multiply by 4, and then we subtract 1. The stuff in this case is whatever g of x was equal to, x squared plus x. Okay, let's just expand that. We get 4x squared plus 4x minus 1. Now let's work out g of f of x. So we are replacing the inner function f with 4 times stuff minus 1, 4x minus 1. The g function in words says to take the stuff and square it and add the stuff. So we take the stuff and square it and add the stuff. It's very convenient when working with composition to think of the functions verbally and to replace x with stuff, because then we can allow for new stuff to be plugged in. So here we have 4x minus 1 is the stuff, and we can expand carefully. We square the first, we multiply these two terms together and double, so we get negative 8x, and we square the last, including the negative sign, to get plus 1. And then we collect like terms, and we get 16x squared minus 4x. And we can see that these two expressions are not the same. Because f of g of x, I'm going to use because, f of g of x does not equal g of f of x. Therefore, the order of performing composition does matter, and we would say that composition is not commutative. Okay. Next exercise. To what does the square root of x squared simplify? Until recently, many of us thought that the square root of x squared was a case where the square rooting and the squaring canceled and we were left with x. But we have seen the graph. We'll just take a look at the graph program. We've seen that the square root of x squared indeed looks like the absolute value of x. If you were to make a table of values, what we could do is say if x is equal to, let's say, -3, -2, -1, 0, 1, 2, 3, then this is the square root of -3 squared. We always have to work from the inside out. So the square root of -3 all squared, well, -3 all squared is 9, and the square root of 9 is, and now we pause. The square root is a function. For the one input, there can only be one output. That one output is non-negative. It's the positive 3. So here we square -2, and then square root. There's only one answer. The square root of -1 all squared is equal to the square root of 1. There can only be one output from a function. And we continue on like this. And so we see that what's happening from the input to the very final output? Well, we've taken the absolute value. And so we have the absolute value function here. Try to get it nice and neat on the number lines. You should be using a ruler on your handout. And over here as well. I think I've got it mixed up. And don't forget to label properly by putting arrows on the axes and X and Y labels. Okay, so the next thing we want to talk about is composition involving square root of x and x squared. Go ahead, pause the video, and try A and B on your own. In part A, f of g of x is a composition of f with x squared. F is the square root function, so we are square rooting this stuff, and now we know that this is equal to the absolute value of x. The domain here is x contained in the reals. And we have the graph of absolute value of x again. Okay, in part B, the graph of g of f of x. Well, let's see. G of f of x is equal to this g evaluated at, or with the square root of x substituted in. And g is the squaring function. So here is stuff squared. And what goes inside here is the stuff of f of x, or square root x. Now, we would think that the square root and the squaring cancel, leaving us with x. But if we check graphically, and we would think that this domain, the domain of y equals x, is x contained in the reals. But let's check with a graphing program. And if we switch the order of composition, well, we had the square root of x squared before. Now let's switch the order of composition, and we have y equals something squared, and the thing to be squared is the square root of x. So we're switching the order of squaring and square rooting now. If I turn off the blue graph, the red graph is in fact not the line y equals x, because the line y equals x has a domain of all reals. But our function only has a domain of x greater than or equal to 0. So the domain is not what we think it is. This still simplifies to x, but the domain turns out to be only when x is greater than or equal to 0. So we have to put that domain restriction along with the function, and then we draw the function as... I'm trying to draw them on the same, but I want you to see the two different colors. So this is y equals x when x is greater than or equal to 0. And you can type that into the graphing program as well. Y equals x, comma, x greater than. I can't put equal on the graphing program. No, we just have to know that the endpoint is included. Okay, well, let's see why this is. How are we going to know if the domain is the same as the original or something different? The domain of a composition, then. So we know the domain of a sum, difference, product, or quotient. Now the domain of a composition, we have to be careful. The actual domain of the composition is the domain of the simplified function after composition. So that would have been the x. That's the simplified function. So after we simplify the composition, we just got x. But we have to take the domain of the simplified function and we have to intersect it with the domain of the inner function. Well, the inner function was the square root of x. And the square root of x has a domain of x greater than or equal to 0. So when we put the all reals with the domain of the inner function together, we get the actual composition function's domain. So let's try this again. Determine the domain of f of g of x, where f of x is this and g of x is this. Okay, so our f of x function, our f of g of x function looks like the f function with the square root of 9 minus x squared substituted in, and f is the squaring and then subtracting 9 function. So square, then subtract 9. What goes in here is the stuff, the square root of 9 minus x squared. So when we simplify this, we get 9 minus x squared, subtract 9 is equal to negative x squared. What is the domain of negative x squared? Well, thinking of the graph of a parabola, we have a vertical reflection on that graph, but the domain is all reals. We also have to consider the domain of the inner function. So let's do this in two pieces. The domain of the outer function, or the simplified function, domain of the simplified, or that's what I called it, simplified function, intersecting with the domain of the inner function, in this case is g of x. So let's get the domain of each of those separately. The simplified function has a domain of x contained in the reals. The inner function has a domain restriction of radicals must be positive or 0, so we know that 9 minus x squared must be greater than or equal to 0. Let's just remind ourselves how to solve this carefully and correctly. If we are solving 9 minus x squared greater than or equal to 0, we can take the x squared to the other side and consider solving graphically. This says that we want the parabola y equals x squared to be lower or the same height as the horizontal line 1, 2, 3, 4, 5, 6, 7, 8. Oh, I don't know if that's 9 or not. Let's call that 9. 9. There are 2 points of intersection at x equals negative 3 or positive 3. We want the graphs to be equal in height, so we want to include those endpoints, and we want the red graph to be lower, which occurs between. Similarly, we want the blue graph to be higher, which occurs between. And so the solution of this is negative 3 less than or equal to x less than or equal to 3. But that's the domain of the inner function over here. So the domain of the inner function is x contained from negative 3 to 3. So when we put these two things together, the domain of the intersection ends up being x contained from negative 3 to 3. Well, we know a picture is worth 1,000 words, so let's actually draw the graph of this and draw the graph of this, because this is not exactly the same as this. This has no problem with x being negative 4, for example. But this expression does have a problem with x being equal to negative 4. If x is negative 4, then we get 9 minus 16, which is negative 7, which cannot be under the square root. And according to the very original statement, we have to work from the inside out, so we have to consider the x values that are acceptable for under the square root, not just x values that are acceptable for the final result. So let's take a look at this graph and see how they differ in domain. Y equals negative x squared, you should be able to picture it, is a concave down parabola, and x is contained in the reals. Meanwhile, the graph of y equals the square root of 9 minus x squared, quantity all squared, minus 9. If I turn this graph off, this graph is, well, it looks the same, but it stops. And it stops at x equals negative 3 and positive 3. Whereas this graph does not stop. So it looks like these two expressions are equivalent, but in fact they are not. They are only equivalent from x equals negative 3 to positive 3. So we do have to be careful of domain. As a general rule, when working with any function, know its domain before you proceed to do anything. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.